And thank you all for being here. I appreciate you all coming. I know you had a choice of tracks today and that you chose this one. So, I appreciate you coming to this talk of all of them. Exactly. So I feel like today what I wanted to talk about is AI voices and AI voice generation. Excuse the popping there. I think of this time in history really as sort of a sonic boom, right? There's a boom of voices. It's a very exciting time to be here. I had some voices that wanted to be here with me today. They were unfortunately unable to attend just simply due to time constraints and trying to get across the internet in time to be here. We may hear from them later in the talk. I also thought this was a great pun on Street Fighter, although I'm not entirely sure. Raise your hands if you actually played Street Fighter 2 at any point in your life. Okay, so everybody knows who's got. Okay, so the Guile joke hopefully will go through. I didn't pepper this with Street Fighter references, although I might have, so you'll see. So what I wanted to talk about today really was speech synthesis, so like where we started from, how we got to where we are, and where we're going, right? So what we got to start with is why, what's the OG speech synthesis system? And it's the one that we all use all the time, right? This is just the normal human elements here. All of these pieces work together to create any kind of language that you make, right? So you're talking about pushing air through your lungs, comes out through your tongue, your lips kind of move around, your nasal cavity, and you make sort of like nasally noises like and all those kind of things like that. The velum is a flap in the back of your mouth. You can kind of open and close, you don't recognize it, and that actually allows you to do sort of like more breathy noises. My mother-in-law is actually a speech pathologist who worked at the University of Washington. And so we've talked for a long time about how little kids learn to speak and how long it takes them. And if those of you who have kids know that it can really be a challenge to learn how to talk over time. It requires effort, and some people have speech impediments. They have to work through them. So it's not surprising that it took us quite a long time to get to the point where we could actually make machines talk vaguely like we can. Because it takes humans a long time. It takes humans years to figure it out. So it's not surprising that we can. And the thing about this that I was told by my AI friends was it's really gross because it is based on meat. They don't find meat-based sounds that appealing. They prefer to use more interesting models of how they do it. So what are the actual representations of speech, right? So you have things called diphones, phonemes, triphones, phones. What those are basically broken down parts of speech. So everything from like glottal stops, to all the way to vowels, to any kind of little part of speech that you can break down. Those are all segmented out, and there has been a lot of research and a lot of work on how that speech is then put together again. One of the first ways that people tried to do this was that back in the early 18th century and 19th century, they actually had mechanical things that could emulate the human vocal tract. They could actually push air through stuff. If you look on the internet, you can find weird sounds where these sort of breathy machines are making kind of noises. Then they moved on to this thing called formant synthesis. And what that was they realized they could just basically take tones and allow them to be modulated and put together to actually approximate certain phonetic sounds. But that was all very hand done. So what they did was basically take a lot of the sine waves and everything else and combine them manually to be like, all right, here's something that sounds like a v or a k or a d, and then had somebody listen to it and tune the parameters of it for a while and move it around. Finally actually created something that sounded vaguely okay. That was sort of the state of the art for a long time. That was one of the big advents and advantages at the time was they could actually do the sort of mechanical generation. It sounded okay. The next step beyond that was something called concatenative synthesis. And that is the one that we somewhat know today. That was where they took pre-recorded speech, broke it up into all the different sorts of levels, and then just stuffed it all together. This is the one, it goes through kind of these steps. There's an input text. So you have hi, I want to be here today. The text analysis, what that does, this previous one, the format one, was really just it took the text, and so they had to kind of manually kind of make, there was no text to, in format, there's no text to speech really. It's sort of just got to make the tones work manually. This one, you can actually take input text. What it would do is text analysis, sort of the normalization, linguistic analysis on that one, where you really could take it and figure out, okay, what is this speech? What does it look like when you break down the words? Then it would do a phonetic analysis where it took all of those and turned them into the phonemes and the different diaphones. Then it would basically look it up in a speech database. And you probably had to have hours, tens of hours, hundreds of hours of recorded speech to figure out all the different noises. When they were doing Siri, this is how they first built Siri. Siri was built using concatenative synthesis. They just took, I think her name was Susan Bennett? I forget, yeah, I think it was Susan Bennett. And they took her and they recorded everything from saying phrases from Alice in Wonderland all the way through the entire alphabet and then all the way through encyclopedias and dictionaries just to get every possible version of her voice. And then they had to hand tag all of that. Some bunch of guys sat around, a bunch of people, and just chopped it up and looked at every little phoneme and every little vowel and tagged it. So that's how Siri sounded reasonably good when she came out. And that was an incredible amount of work, right? You can imagine how much of it. And also, it only works for one language, right? The earliest version of this you probably all recognize as DeckTalk. DeckTalk was the first actual real successful speech synthesis system, and it's the one that Hawking used, right? So it became very, very famous because of Stephen. It utilized one of the big things in this one was this is a later version that you ran on Windows NT. This is the entire processing thread here. Nothing really much happens here. Application, text queuing, not a big deal. The command parser. Letter to sound thread was very interesting. They talked about because they basically discovered while trying to build DeckTalk that, again, English, like all languages, has a lot of words in it that do not sound the same when written. As you all know, there's sought, the units of sought, bought, but then all the different ones that sort of have homonyms that are similar. So they had to have basically a 15,000 plus word library of things that would be pronounced one way, but actually are pronounced a different way. And that became a major part of the library, was just making sure that the thing that was trying to be written was said in a way that sounded correct to an English listener, when actually it was not written the correct way. And then he got into the phonetic and prosodic processing libraries. Prosody is the way of intonation. So when you actually put emphasis behind something, or you have emotion, like I'm super happy or I'm really angry. All the prosody in here was something they had to sort of encode. That was not something that was there. If the voice didn't have it, they could not make it again. So unless Susan went and recorded just being incredibly pissed off all the time, they wouldn't be able to really tune that too much. So they had to kind of take what they got. And they would do the vocal tracks, but it was actually pretty good. This thing doesn't play sound, does it, guys? I can't play sound from here, or will it play sound? There's an aux cable? Okay. Oh, I see it. Okay, so I'm going to do that in a second here. So there was actually, let's go, I'm going to do a dangerous demo here. So, Bodhi, we're going to bail out of this for a second. And pray to God this works. Let's see here. DeckTalk. So, let's go to here. You can't see this, maybe you can hear it. So there's actually a MAME emulator of an old DeckTalk speech synthesis system. So you can get in here and you can actually run it in your browser. I don't know why you can't see it.
DeckTalk version 2.0 is running. And we are fault using factory settings.
Great. Hello? No?
Hello, ClueCon2023, hello.
Wait for it. Wait for it.
I am excited to be here.
There you go. So, that you can kind of hear it in the back. You can hear it kind of putting the pieces together. So back to this guy for a sec. So that is, and I don't know why you can't actually see it on the screen, but that's fine. It doesn't matter. View, home. Go, I can't get back to the slides. How do you get back to the slides? Here we go. All right, great. So that's one of the DeckTalk guys, right? That is something you can run in your browser right now. It's actually kind of fun to go back and listen to it do stuff like that, but it doesn't actually sound, it sounds like Stephen Hawking always sounded. And that took us a long way. That's what we did for a long time. That was as good as it got, right? That was when we grew up in the 90s. For those of us who were alive in the 90s, which is, I know, not everybody in the room, which is a crazy thing to think. But that was where the state of the art kind of was. And then it kind of got better, right? We had different tools after that. A lot of people here have used Festival and open source tools to actually make TTS sounds. But what do we really want? Well, the next thing that arose after sort of concatenative synthesis was this, statistical parametric speech. So the first paper on this came out in about 2006, 2007. And this starts to be the basis of what we're using today. And so what are we trying to do here? So effectively, it's like, okay, we're still trying to go from text to text analysis to the generation of the features inside of it, and then generate some waveforms. That's fine, and we're going to use a vocoder in the middle here. So what are we doing over here in linguistic features? Well, basically, that's just linguistic features are just the text compiled from the analysis stage. We're again breaking them down into what are the components of this text in phonemes and phones, diphones. How do I make this? What is this supposed to sound like? And the feature generation in the middle there, the feature generation is the part where it's like, okay, now I want to do stuff like maybe talk about the prosody, vary the cadence, maybe change the tone or the pitch or something like that. That used at the time, the original papers came out, used hidden Markov models, which are a statistical method to figure out probability over a certain time domain. Because speech is a thing that happens over time, right? You can't just analyze speech at a given point. You have to analyze it over a time function. So hidden Markov models were a way to look at that statistical probability over time. And then they went through the vocoder. So the vocoder is an interesting part of this too. So now what have we done? We've taken text, we've analyzed it, we've moved into the feature section here. We're kind of like statistically looking at the way the text actually works and how it might vary over time. And then you have to get into the vocoding part. The vocoding part is in itself. I broke it down. I kind of blew it out down here a little bit. So this is just the vocoder sort of blowout. The reason why here is that whole piece is in itself a giant piece. So the feature generation is huge and the vocoding is huge. The vocoding, if you wanted to do one vowel, I put it down there. So let's say we're doing a high quality sample of 16 kilohertz. You want to do 80 milliseconds of a raw waveform, about the length of a vowel. You're really going to hit about if you want to encode that vector, it's about a 1280 dimensional vector just to do 80 milliseconds. So as you can imagine, that's a very, very large vector. Now, that might sound similar if you're in AI stuff today, because that is a similar vector length to what you used if you're getting an embedding from ChatGPT. It's something similar to that. But it's a very, very large amount of information for 80 milliseconds when you're talking you want to generate audio for potentially seconds or minutes at a time. Way too much to deal with. Basically, the computers couldn't handle it at the time. There's just too much data. So what did they do? Right? What did they do? They basically used a bunch of different compression mechanisms in the vocoders to say, we don't need to actually look at all of these vectors. What it would do is assume, okay, when you're talking, you actually don't vary things that much over a certain span. Let's say 30 milliseconds or 90 milliseconds or 100. So take that, assume everything's basically static for that amount of time. So suddenly you don't have to analyze every 80. It's just some sliding windows of 30 or 40 every 100 or whatever you want to do. So it just reduces the dimensionality, reduces the complexity of the entire problem. And that's great, because that allowed the computers at the time to actually do this work. Otherwise, they were unable to do so. But the people at the time and the scientists knew there were better ways to do this. They knew the holy grail here was to just go from that to this. All the middle steps, they were starting to realize that trying to analyze text and make it sound more like the way we produce sound, like by is not really that successful. You don't want to do that. You want to go right from the text and go directly into a speech waveform. So what did they do? Oh, excuse me, gosh. Basically, that was when Tacotron 2. That was basically what this did. So if you guys, whoever was in here who remembers when this came out, it was kind of a big deal. Tacotron was basically the first neural sort of deep learning system that went directly from text and went through the character embedding. So it didn't use any of the phoneme analysis, it doesn't use any of that kind of linguistic analysis. What it does is it dumps it all into a bunch of neural nets. So it dumps it in an LSTM up front. The LSTM replaces, so that LSTM here replaces this piece. That replaces the text analysis and feature generation stage. That is this LSTM stage. So it does all that stuff sort of right there. And then it goes over sort of all the way through, and what it then generates is a MEL spectrogram, right? So the whole point was they were like, a MEL spectrogram is basically a log analysis of frequencies and ranges over time. It's what audio engineers, and a lot of you probably had no MEL spectrograms or at least seen them. So it can generate the entire Mel spectrogram just by looking at the text. There's no need to go and do all of these intermediate steps where you have to do so much logic and thinking. You just put it into a trained net that has been taught how the text should look from looking at previous Mel diagrams, and then puts that into the WaveNet. And then WaveNet was the other part of it. So the Tacotron is a combination of Tacotron was the combination of an LSTM sort of feature extraction mechanism and the WaveNet guy up here. And the WaveNet one is the one that actually takes the Mel and generates the actual voices. That's the vocoder. So WaveNet was the vocoder, and Tacotron, the entire thing was all of it put together. And the examples from it at the time were kind of amazing. They really did sound incredibly lifelike, very, very natural. This was 2017, I think. I remember I gave a talk on this in 2018, being like, we're almost there. Like, you're going to clone your voice tomorrow, and we're all going to sound like James Earl Jones, and it's going to be amazing. Turned out that the samples they gave when this came out were pretty cherry-picked to make it sound amazing. It was harder to make Tacotron work at scale than we thought, or that we wanted. And that was fine. But it did prove that this method would work. You could go right from text directly to audio without any intervening steps, very clearly where the future was going. So it all just took a little AI, right? All it took was a little bit of AI in there, and then they said the computational power behind it to power these neural nets and the training and the data. It was fun stuff. And then, so nowadays, what are we up to? So now, again, it all comes down to like generative stuff, right? So again, this just turns out, as we a lot know in AI work, it's a data problem. They needed more data, more training. The models got better. More papers came out that allowed this to sort of like link up. So the most recent one that came out is one called Microsoft VoiceBox. This just showed up, I think, a few months ago. These are, if you go look at papers coming out in the speech world, it's just crazy. Like every 3 months, somebody's putting something else out. What they're not doing anymore is releasing the code for these, which is annoying, because they've been scared now over the past couple of years about the idea of voice cloning and people be faking people. I don't know if you guys knew about the one in Australia where somebody faked being from the Australian power company and started calling up people and saying that like, we're going to shut off your power if you don't like pay us today. But it sounded like a normal Australian guy, and it just duped like a couple thousand folks in Australia. It sounded so good and was able to react in real time. So they're right. Like this stuff is happening in the real world right now. But the way this works is VoiceBox just uses like a generative model, like everything else, using a lot of the same LLM technology, using ChatGPT, but it does a bunch of stuff in the middle now. Now we do things like built-in denoising, because one of the problems is we didn't have really clean audio. Your voices would sound crappy, and so you have to denoise it. So it does that for you. So, you could take somebody just talking randomly and denoise all of it. Goes through the raw data. You have the zero shot TTS. If you don't know what that term is, it's the idea that like I don't need to have more than a couple seconds of your voice to make it sound exactly like you. And I'll show you an example of that in a minute where I used 1 minute of mine. And then text-only sampling. You get it here, just dump it in here. Again, Mel spectrograms. See, it's all doing Mel, all spectrograms all the way through. So we're going right from text all the way through just to the audio, and it's kind of incredible. So let me give you now a demo of that for a sec. So this is my voice that I just did right before I came down here, which is why I walked in at the last possible second. So thank you to the AV team for accommodating me just coming right in here. So this was after 1 minute of me talking upstairs in the room. Let's see.
I'm absolutely thrilled you're all here to hear my talk. Thank you so much for coming.
Let's see here. Such an amazing conference. Boo, 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 boo. Bam. Bam. So I'm generating it right now. I just hit the generate button. I just type like a sentence of text.
I would like to thank Anthony and the entire ClueCon crew for throwing such an amazing conference.
Sounds pretty good, right? And you could generate, that was just me, talking into just my far field mic. That is one of the models that came out last year, and that took a minute to do that, not a problem. They now have more premium features, and I'm going to go, I used that one was done through a company called, that was done through a company called, both 11 Labs and Play.ht. Both of those have like immediate voice cloning. If you want to pay more, you can get like premium voice cloning. I didn't want to pay, so I didn't actually do that. But you can get really, really good stuff. These are the commercial companies right now that are kind of leading the field in this. 11 Labs, you've probably heard of them. They're very popular and have a lot of funding. Play.ht is an interesting one that I'll talk about in a second, because we need to talk about the open source stuff first, because they actually are using an open source one and have now elaborated quite heavily on it. Well Said is a commercial company out of Seattle. Murph.ai is another company that's been around for a long time. These are all amazing AI TTS providers. You can use any of them. They all sound great. And it's basically an arms race. Like, this is a picks and shovel problem. These guys are all incredible. I would advise just going and using them. And they are dirt cheap for what they offer. It's almost insane. But they are cheap because of us in the open source community. Look at these things. These are great. You want to run it yourself? Go nuts. This guy over here, and I know if you want to know more about this, go talk to Zoa. If you haven't seen his talk, or when you go talk to him, Zoa knows a lot about this as well, from Bonafo, because he's done quite a lot of work. But these are some of the new ones. So Tortoise TTS was put out by a guy last summer. Tortoise is a generative AI model that can actually do voice. I would show you an example of it, but it does take like a couple minutes to run. I think he actually just released a new version of it that's like 10 times faster. But Play.ht, these guys started with Tortoise. They were a Tortoise company that took it last summer and ran it and basically hired that dude to help them sort of optimize it. They now have a new model that is actually much better. But they used that originally. You can still download it today and use it, and it does sound very, very good. And what's great about the generative models is that I can take my voice, combine it with Tony's voice, combine it with all of your voices, and then make entirely new voices. Like, they are completely synthetic. They don't sound like anybody. They kind of sound like maybe a mixture of people, but it allows you to have sort of things like a custom brand voice for a company. So you can offer, be like, oh, you want your own voice that only you have, and you own the rights to that one voice, and you just tune some parameters or add a couple other voices into the mix and generate something really interestingly new. Valley is a new one from Microsoft that came out in the spring, and then instantly sort of people took it up the paper. Again, they didn't release the code for it, so it's a little bit behind, but that was taking a 3-second sample and having it sound incredible. Again, we have VoiceBox here. Microsoft just released this one. These guys are working on it over here. I think it's Stability.ai is paying this guy Lucid Drains to create a VoiceBox open source program, so go use that one. Koqui is a giant framework that you can download and use, and it has all old school TTS, the traditional sort of ones you recognize from every IVR, as well as a lot of the newer deep learning stuff, and Bark as well. Bark is another one of these generative models. All of these available today. Go check them all out. They're all incredible. You will see, though, that sometimes it takes a lot of those of you who have run AI. It takes quite a bit of CPU to do this. So you might just be better off more economically just to use one of the commercial providers, unless you're trying to do something at scale. Because the GPU required to actually get these generative things to work is not insubstantial. So don't think you're saving a ton of money here. What's good about them is it does give you a ton of flexibility to experiment and play with how you can incorporate these into a product or into some sort of like workflow, and then be like, okay, great, now we'll use a third-party provider, understand the limitations they have, what we could do. So I encourage you to go check all of these out. And then go check these guys out. And I'm not paid by these people. I just think they do cool work. And yeah, so that is where we're at right now in the state of voice. And I think where we're going to be in the next coming years, and you've seen this if you played with any of these, is the voice cloning now with a minute. You'll have the zero-shot capability that's going to be here by the end of the year, right? The ability to take like 1, 2, 3 seconds of audio and just dupe anybody like that. And so as we talked about the AI roundtable yesterday, there will probably be regulations. I know I do live in Santa Monica, so like I have friends who work in the film industry. There is a lot of that talk now about how do we protect voices. I was at a talk from DARPA like 4 years ago, and James Vanderbeek was there, and I remember talking I mentioned something in an elevator, and I was like, oh yeah, in the future, like AI voices are going to take over everyone's job. Are they like going to replace everybody? And Vanderbeek literally like from the back of the elevator goes, hey man, don't take my job. And I was like, don't worry, James, I think you're fine. But it is a real concern for younger actors. If you go on and talk, one of the things that the SAG people are worried about is they'll go on, someone will say, they have one of the contract things, clearly a maneuvering mechanism for the companies. The they had a thing for the waiver saying if you're a background actor in any movie, you give away your right immediately to be used in the future in anything else, just your visage and also your voice. So imagine you have a young kid who comes in, gets cloned as a voice, and then becomes the voice of Volkswagen or Buick or Ford, and they pay the guy $20, and then how fair is that? But then again, they could just generate their own artificial voice. So it's going to be a very interesting world of audio that we're sort of moving into. Customized audio, all sorts of fun things. And audio is a phenomenon that we are all intensely familiar with, being in real-time communications, and the fact that we know that it's a very unique space. So again, I encourage you to get out there and play with it, learn how the future is evolving, be a part of it, be a part of these communities, talk about the legislation, like Jeff was saying yesterday, make sure we work in protections for people, but then also allow us to keep experimenting, because this is not anything that's ever going to go back in the box. And it's a great place to be. So thank you all so much. I really appreciate it.
Thank you, Evan. Thank you, sir. There is time for a couple of questions for Evan. So if anybody has a question, just raise your hand. We'll get a microphone. There's a gentleman there with a question. A microphone is coming your way, sir.
Hello. Hello.
Hey.
Yeah, with the advent of generative AI and now that we are able to generate voices exactly like humans and exactly like a particular human, right? Mm-hmm. So how do you see that is going to affect the voice biometrics applications where we want to authenticate the real human being and the exact person that we want to authenticate?
Absolutely. So voice biometrics are going to have a real hard time here, right? This is something that you're going to have to basically start augmenting with other biometric. I'd be surprised if voice biometrics alone survive this shift. So generally, it's going to be some sort of 2FA. The voice biometrics might be part of it, because having a clone of David, as much as I would love to have it in my back pocket, I probably don't have. But David, I could probably take his voice, use it for something like calling a bank, but then that's why you have a 2FA key on your phone or something else that David physically owns that I can't just copy. But it's true. You probably, at this point, shouldn't necessarily listen to somebody over the phone or anywhere else and think it is necessarily who they are. Maybe you should just start giving one-time pass keys to your friends. So, what's the code word? Banana.
Yeah, it's a very interesting thing, isn't it? Because when you think about who you are, something you know and something you have, who'd have thought that the who you are part would be the part to get replicated?
Right? It's crazy.
That's a crazy thing. Thank you for that question, sir. Any other questions for Evan while we're here? Yes, just there. Thank you. Microphone coming your way, sir.
For the system requirements for running the model, is that for training, or is that for also using it in just doing text-to-speech?
So for the actual production, it is that's the hard part. So like the Tortoise model, at least the one that was running at the end of last year, or the beginning of this year, would take about 2 to 3 minutes to do a couple sentences.
Oh.
So it's actually the actual running of it requires the actual high. That was using like a one of the T1s over on Google Colab. So a fairly low powered GPU, but still something in there. It's not a real time. This is something I should have probably touched on as well. A lot of these generative ones are not real time systems. Some of the newer commercial ones have been tuned to be real time. But real time, let's say the Play.ht guys, they just released a new model, I think 2 days ago, that is now able to generate a lot of this stuff in 800 milliseconds. Which is good, but it still might not be fast enough in some cases. I know that 11 Labs has a real-time API as well, so they have one that does it, but their best stuff also is not there. So if you have an opportunity to use what I call slow time audio, where you can actually take the time to do it, you can make it sound incredible. If you have to do it in real time, you're going to sacrifice some quality features. That will get better.
Okay, thank you.
Yep.
Do you feel your question was answered there, sir? Good. Okay, we've got time for just one more. And Jeff, if I could call you up to get connected up, that'd be great. Got time for one more question, if there is one out there in the audience. But I'm not seeing one. So let's say a very, very big thank you to Evan.
Thank you, everybody.